Welcome back. In the last session, we talked about the EM grades, and now we are going to talk about the supporting films. So, in the EM grades, we have discussed about the mesh grade, we have discussed about the slot grade, and we also discussed about the quantifier grade. So, now in this session, we are going to talk about yet another specialty of grades. So, these two grades, namely the holy grade and quantifier grade, that will come soon. These holy film and quantifier grades, they are a special types of EM grades with the normal mesh grade. You can see a mesh grade on the top of which a film is coated on it. So these films are called, the grids are called a specialty grades, the holy grades and the quantifier grades. So I'm going to give you a detailed outline of how to make the holy film at a later date time. The quantifier grades is going to be a commercial one, and they are like, since they are patented ones, you cannot literally make them in the laboratory. So let's see the holy film and with a carbon coating on it. This is called like a holy film carbon grade. Colloquially, people call this as a holy grade. So the holy grade will have the regular mesh grade. The mesh can be, as you discussed in the last slide, it can be a square, a hexagonal, 475 mesh, or whatever it can. And on the top of which there will be a thin film of the holy film is just suspended on it, or just made a coating on it. And when you viewed into the electron microscope, this is how it looks like. It will have the holes of different sizes, different shapes, and different locations. So this has some applications on it. So if you just look at this holy film alone, there is a plastic film and there are some holes here and there. So these holes find their applications, especially in the cryo-EM, and so that is one of the applications of the holy film. So holy film has the applications in the cryo-EM, and also it has the standard tool for correcting the astigmatism. So these holy films are routinely used, and these are also commercially available. You can purchase them from the commercial vendors. And the good thing with this holy film is you can make them in the laboratory, bringing down your cost of procuring the films to something like 100 volts. So shown here are two examples, and you can see here this is the scale bar. This is the point that you have to keep in mind whenever you are just producing the micrograph. This is what we call as a micrograph. You need to show the scale bar so that people can know the dimensions of the objects they are seeing in the micrograph. So as you can see from this, the holes are of different dimensions, ranging from something like a 1 micron to something like 100 nanometers, or maybe there are some holes even smaller to that. So this is one type of arrangements, and you can see here these holes are closely packed here than this. So these are all different ways of producing the holy films, and that we'll discuss in detail later. So the take home message as on now is the holy film is a regular mesh grade on the top of which there is a layer of holy film deposited on the grade. The holy film will have the holes of irregular shapes, irregular sizes at irregular locations. So everything is irregular here, but still it has a regular application by means of taking as a screening cryo-EM experiment, and also a tool for correcting the astigmatism. Let's move on to the next part, the holy film. Holy film is also a square mesh, as you can see here, a mesh grid, on the top of which there will be a coating of the carbon film laid on it. But strikingly, you can see the holes that you are going to see in the quantifier grade are uniform size and uniform dimension. Of course, uniform size, uniform shape, and the spacing between them are perfectly aligned. So this has at another application, like just like this the holy film, the quantifier film also is going to have the holes there, but the advantage moving from the holy film to quantifier film is the periodicity of the holes and the regularity of their dimension. So this will make the quantifier grid suitable for Kayomi experiment, just like your um, holy films, but this also helps us to go for what is called automation. So what is that automation means? Just focus on this whole and just make a small program that once the program is done, just make a translation by what is called the hole spacing. What is the hole spacing here? The spacing between the two neighboring holes. And what is the hole diameter? The diameter of each of the hole that you are seeing here. So these are all like a very particular numbers fixed for a given holy film. So once you know the diameter of the hole, you can just take the image at the center of the hole, so that you will be focusing only at the center, and then make a program that the beam will make a translation, or the film will move to a different location, and then the image is taken. And since the spacing between these two holes are uniform, you can just program such a way that each of the image will be taken at the different holes, and once it reaches the end, make a translation and then reverse back, so that you can just track all the holes again. So this quantifier will help us to automate the program. So that means maybe on one Friday evening you set up the cryo EM experiment, just set up at one of the hole and program that it has to scan at every regular intervals, and just once reaches the end of it, make a translation and then go in the reverse direction, go home, come back on Monday, the all the holes in the quantifier will be scanned and your data will be ready. So such is the convenience by going for the quantifier, and never ever imagine this kind of comfort when you go for the holy film. So that's the difference between holy film and the carbon film. ఏంటి ప్లాన్? సరే ఎక్సర్సైజ్ చేసుకుంటావా అట్లా క్లాత్ మీద? సరే నేను ఇంకొక స్లైడ్ చేసుకుంటాం. Now let's move on to the support films here. The support films, as we discussed before, it acts as a substrate for whatever the specimen that you are interested in, and it should be a thin, electron transparent, and strong. So the material that qualifies for thin, electron transparent, or the strong material are the plastic films. The plastic films made of either collodion or the foam war. So the support films are of two types. One is a continuous plastic film. The second one is a plastic film that has holes in it. So just now we discussed about two varieties of the plastic film that has holes in it, namely the holy films and the quantifier films. Now in this one we are going to discuss about the continuous films, how to make them, and what are the advantages compared to each other. So as just now said, there are two varieties of the continuous films available in most popular way. One is the collodion films and the other one is the foam war films. So let's look at this. This is the collodion film, and let me just tell you this: the collodion films and the foam war films can be commercially available, but if you make them in the laboratory, they are like a very simple and easy process. Once you just have the technology and the procure all the necessary things for making the films available in your laboratory, you can just make them when and where you want. You that way you can reduce the cost, you can reduce the waiting time. So both of them are very important in research: the cost and the research, the waiting time. So basically the collodion film is made of a collodion, which is nothing but a cellulose nitrate, and this part we'll discuss about this in a minute. Let's see how the arrangement goes here. So this is typically a Buchner funnel. A Buchner funnel typically looks like this. So this is made of a porcelain with a holes, just a periodic holes, just made in a concentric circles here. So what is the purpose of this is, when you let the water go, any film that deposits on it will have a uniform motion downwards, so that there is not going to be any vortex formed here. So instead of this, instead of a Bushnell funnel, if you just go for only one opening, you know it's going to form a well-like structured arrangement here, or the appearance here, that will make the film to be broken. So in order to have like a uniform deposit of the film, what we need is a Bushnell funnel. So having seen this, let's come back here. What we will have here is we will just arrange a small stage here, and on the top of the stage we just lay the grades. And take a note, when you are laying the grades, the film that we are going to have will deposit on the grid. So that means the one that faces up should always be the dull surface. If you want to know what is the dull surface and what how to identify a dull surface and what exactly a dull surface means, I suggest you to just go and look at my video on the electron microscope grades. Now, once you have the grades spread along the stage, and the stage is being kept on the Bushnell funnel inside it, what we do is we just fill the entire pot with water. So this has to be done, because if you do the other way, like if you take the water and then put the film on it, the stage on it, placing the film, the grades will be a challenging one. And again, while filling the water, you have to be careful that these grades should not fly away, because the grids are very light in nature. They are prone for flying away as you add the water. A little disturbance is enough for the grids to displace. Now, on the top of the water, what you have to do is take 2 to 3% by volume of the collodion dissolved in the armyl acetate. This is an organic solvent, you know that. And once this is dissolved, take a droplet of it and just leave it. Because of the surface tension phenomena, the drop spreads over the surface of the water, and since the acetate is an organic solvent, it will just evaporate, leaving you the film of the collodion on the surface of the water. So once the film is deposited on the surface of the water, let the water go away, because there will be a stopper here. And once you release the stopper, the water goes away. And because of the several perforations here, the film will make a uniform movement, and this film will go and sediment on the top of the grates. So once the all the water is receded, you can take the grids off, and that can be dried off and can be taken for the electron microscope experiment. So this is one very convenient and cheap way of just making the collodion film in the laboratory itself. Few precautions has to be followed. So you know what, if you don't take a proper precaution, what you get is a crap. And you know the rule, garbage in, garbage out. So in order to just have a quality film on the grades, you need to check the quality of the film that is being deposited. The first one is the water you are taking should be doubly ionized, or the millipore water, and it should be free from any of the dust particles. Then the film that you are just using should be uniform and should not have any breaks on it. How do you check whether any breaks are there or not? Take any fluorescent screen and just scan on the surface of the film that is formed. If you see any cracks, just like the way that you have noticed in the ultramicroscopic experiment, any crack, the presence of any crack, let it be even at microscopic scale, will produce some fringes here. So that means the appearance of the fringes on the top of the film is an indication of the breakage of the film. And if you notice any breakage here, discard this. So how can it be discarded? Just take a tweezer and just hold it and just remove it. So make sure the film that you are using is continuous and free from any breakages, and that only will lead to sediment on the grids that you are using. So one. Second, whatever the precautions that you have taken, let the water be pure millipore and the grids are freshly laid. The usual practice is first droplet, the first film that is deposited using this combination has to be discarded, because even if it is of good quality, the people suggest to just discard the first film. The same logic as we did for while discarding the first set of sections in the ultramicrotome. So this film usually what happens, it will just accumulate all the dust if at all present in the water here. So if you just discover this film will take away along with it all the dust particles, so the next film that you are going to lay is believed to be free from all the dust particles, and that can be used for sedimenting on the grids. The precautions, the film should be broken from, like free from any breakages, and the water flow that you are letting out should be as slow as possible, because any fast movement will disturb the continuity of the film, and disturbance of the continuity of the film will result in the grades, and you know what it carries on further forward. So that's about it. And then what about the strength of it? This is relatively unstable compared to the other counter version of this, that is the foam war film. And because of the slight instability of it, you have to go for thickness of 40 to 50 nanometers. So that means it is adding a thickness of its own to the strength of the sample, and thereby decreasing the resolution of the image. Remember, the thicker of the specimen, the resolution is going to be lower. So this is the concept that we discussed several times. And I told you about like what is the need of going for the dull surface up. So that's about the collodion film. Here is the way how to form the foam war films. So the setup is similar to what we have seen in the collodion films. We have the Buchner funnel, we have the stage on the top of this, we have the grids just aligned here, and we have the water bath here, and we have the stop clock here, so that you can just control the water flow, and everything is similar except the arrangement here and the material that we are going to use. So let's focus on this first. So in place of collodion, if you recollect, we have used collodion suspended in the organic solvent. Here we are using 0.3 to 0.5% formware, which is polyvinyl formol suspended in chloroform. Again, chloroform being organic solvent is known for evaporating quick, and once it is exposed, it will just leave us only the formware film on it. So now everything is similar to there, only the difference is the formware is dissolved in chloroform that is being used to form the film here. So if you just compare, the stability of the film is much stronger, and thereby requires the thinner thickness of the film. That means like 25 to 30 nanometer thickness is sufficient for the formware films. So if you recollect, this was almost two folds when you were talking about the collodion films. So now let's look at the way how it can be done. So what you are seeing here is a microscope slide, which is a rectangular one. So what we do is we take the clean microscope slide, if required, just clean it with acetone and just wipe it out with a damp free cloth. Then just insert this microscope slide in the solution that is having 0.3 to 0.5% formware dissolved in chloroform, and then lift it vertically so that the excess of the solvent will just drip off. So this is similar to just removing the excess of the water from it, and just swipe it in the air for about like a 2 or 3 minutes. The chloroform will evaporate, leaving you the formware film coated on the microscope slide. So then just keep it on a dry surface and take a razor blade and just make the scaling around the rectangular shape of the film. So that means if you just draw a scale around the rectangular film, what you can see is the film which was continuously coated on the microscope slide will be just ripped off, and only a part of it set aside or isolated from the rest of the continuous film. So in such case, if you just start sliding it at an angle with a optimum speed, the film that is isolated with the help of the razor blade starts floating on the surface of the water. The F here stands for the film, W for water, G for grids, S for stage, and C for the stop clock. stopcock. So now once it just starts floating, the film starts floating, everything else is the regular way. So once the film just floats at the right on the top of the grids, let the water flow, and this will make the film come and sediment on the grids. So this procedure is what we call as the Valentine's method. Take a note, Valentine is not a philosopher alone. There is another Valentine who is also a scientist. He was the first one who introduced this technique to the world. So apart from this, you can even use the droplet approach as well. So that means you can just leave a droplet on this, that droplet spreads along the surface of the water, and that can be made to sediment on the grids as well. So this is a different approach. So that means this Valentine's approach don't have to be limit for formwork films. It can be used for collodion as well. On the other hand, the using of the droplet to spread on the surface of the water, thereby forming a circular film, can also be used for the formwork films and in addition to the collodion film. So these are like two different approaches to make a film floating on the surface of the water. So once the film floats on the surface of the water, everything else is a cow story. So I don't want to repeat what a cow story is. Everyone who is just going through and sat in my class before, they know well about what is a cow story is. So the film just comes and settles back on the surface of the grate, and once it sets back after the water recedes, you can take the grates just to dry them out separately, and that can be used. So that's a way of using the formwork films. Now the comparison. So when do you use the collodion film and when do you use the formwork film? I have to say the formwork film is more popular than the collodion film, because a thinner film is sufficient and can give us a stronger support. So with this one, we are done with the collodion films and the formwork films, and next class we will discuss about the Holy films, how to form them, and all those techniques. So next video we are going to have a discussion on the Holy films, and also some details about how to have a carbon film, the necessity of having a carbon film, and how to have it, and the similar concepts. So just to summarize, what we have seen is we have seen the category of the grades, that is Holy films and the quantifiable films, and then we started discussing about formation of the continuous film, which are like two categories. One is the collodion film and the other one is the Holy film. Thank you.